So today we discuss resonance. Okay. So previous class we discussed AC voltage applied on a series LCR circuit. So continuation of this topic and series LCR circuit. So today we discuss what is resonance. That's the very important resonance. Okay. So concept of resonance. Okay. There is a frequency. Keep in mind there is a frequency. Okay, and resonance is the characteristics, okay, of series LCR circuit, and there is a phenomena of resonance among the system have a tendency to oscillate a particular frequency. So the system have to tendency to oscillate a particular frequency. Okay, that's very important. There is a particular frequency, and this particular frequency is called a natural frequency. Okay, there is a natural frequency. Now system driven by the energy source. Okay, and at a frequency near the natural frequencies look like a simple pendulum. Okay, particular frequency, there is a natural frequency, and there is some natural frequency look like a simple pendulum. Like if you see that a pendulum, it look like a oscillation here. These are the natural frequencies. So here to keep in mind the what is the resonance. Resonance means there is some matching between two frequencies called resonance. At that matching two frequency, when they match these two frequencies, okay, there is input frequency and frequency of that circuit. If they match together, then the maximum current will be maximum. That's a resonance. That's a phenomena is a resonance. Okay, the phenomena is a resonance. The system oscillated natural frequency. Okay, there is a system means there is a circuit. Okay, and there is some input frequency, and this match with the natural frequency of that circuit or a system. When they overlap, when they match together, so that time there is a maximum output. The maximum output, and this phenomena is called resonance. Okay. So here in the series LCR circuit, so continuation of previous series LCR circuit concept. So maximum current Im, that is equal to Vm by Z. Z is the impedance, and that's Vm by Z, that is equal to root over of R square plus Xc minus XL whole square. Okay. So what is the Xc? Okay, that's the capacitive reactance. That's the XL is the inductive reactance. And when these two are the frequency dependent component. Okay, so omega is varying a particular frequency. So here if Xc equal to XL, so Xc means 1 over omega C, and now XL equal to omega L. And now so here 1 by LC, that is equal to omega square. So finally we get omega equal to root over of LC. Okay, so that omega is the frequency here, and now this frequency, this omega, okay, these are called resonant frequency. These are a resonant frequency. Now we know that if there is an angular frequency, so there is a 2 pi f, the linear frequency, that is equal to root over of LC. So that is equal to 2 pi root over of LC here. So if I plot the diagram, suppose if I plot the diagram, okay, here is a current I in ampere. Okay, here omega equal to rad per second. Now the frequencies look like this. Graph show this. Okay, now Here is the maximum. This top point is a peak. That's the IM. That's a maximum current here. There's a peak point. Okay. So now these are that a graph, and now here at the maximum point here these frequency. Suppose there is a omega naught frequency. At frequency you get a maximum current. So omega naught is the frequency, the resonant frequency. Resonant frequency. At that frequency we get max current. Okay. So if I increase the frequency, suppose here, suppose these are called, suppose increase delta omega. At this point we get omega naught plus delta omega. Here we see the current is slightly fall. Okay, and suppose if I decrease that same amount, okay, so delta omega decrease, so that is the omega naught minus delta omega at that point. So obviously there is a current fall here. But if you see that at that omega naught we get a maximum current. If a frequency increase, so current value is drop. If also frequency decrease, then maximum current also drop. But at omega naught or at resonance there is a I max current. This point is I max. There's a maximum current here. Okay, keep in mind there is a maximum current. Okay, so take some example. Suppose some example here. Suppose say that example. Suppose say L, we consider a 1 millihenry inductor, and capacitor we consider a 1 nanofarad. These two. So omega, that is equal to, we get root over of LC, 1 by root over of LC, 1 by root over of LC here. So here, so L means 1 into milli 10 to the power minus 3, and nano means 10 to the power minus 6. So here, sorry, nano is minus 9, sorry, 10 to the minus 9. So 1 by root over of 10 to the power minus 12. So 1 by 10 to the power minus 6, half, because root is 2 to the power half. So here 10 to the power 6 rad per second. Okay, and you see that this omega, okay, these are resonant frequency, these are the omega, the frequency here, see that the frequency depend only L and C, not R. Okay, because we know that L and C, inductor and capacitor, both are frequency dependent. Okay, but resistor is not a independent of frequency. That's why in series LCR circuit, these frequency depend on only L and C. Only L and C. Okay, and suppose you say that is maximum voltage Vm equal to, suppose say that is 100 volt, and say the R equal to suppose 100 ohm. Okay, if say R is 100 ohm, so maximum current I max, that is equal to V by R. Suppose V 100 by 100, so that is a 1 ampere current, and this current value, okay, the values of current or magnitude of current, the magnitude of current depend only R and V. Okay, if you say that is same, and say consider is if R is increased, so it was 200 ohm, so Im, that is 100 by 200, that is a 0.5 ampere. Okay, so 0.5 ampere means there's a diagram shown now, starting from this. Suppose there is a 0.5 value. Suppose these are the 0.5, here suppose that 1 ampere. Okay, that's a 0.5. So you see that if resistance in the LCR circuit, resistance value is increased, so maximum current will be decreased. Okay, so look at the diagram, this diagram, and the diagram beautifully represent these are frequency. This x-axis depends only L and C, and the current depend only R and B. Okay, so that's the beautiful things of the LCR circuit. Okay, the resonant frequency depends on XC and XL, and the current depends on the voltage at resistor. Okay, so this resonant circuit, as for tuning circuit, okay, uses in tuning circuits, this resonant circuit, the resonant circuit uses in tuning circuit. Okay, so what is a tuning circuit? A tuning circuit is like that. Suppose there is a black box. Okay, there is a black box. Inside there is a tuning circuit. Okay, a tuning circuit. Suppose a series LCR circuit. A series LCR circuit. Suppose the tuning frequency or resonant frequency, suppose 1 megahertz, and there is a input signal here. There is a input signal here. There is a input signal. There is an input signal. Suppose there is a radio signal. Okay, suppose say that is some frequency. Suppose 98.3 megahertz. Some radio mid. Okay, suppose say that's the frequency of radio frequency FM. Okay, and if that tuning circuit receive 98.3 megahertz, okay, there's the input frequency. Now there is a knob, okay, knob, and you rotating the knob and match the frequency, match the tuning circuit, uh, uh, match suppose tuning circuit, suppose vary. Okay, these are 1 megahertz the tuning resonance frequency. Now to vary of these knob. Okay, these are the vary with these knob and match these. Okay, match these omega naught with 98.3 megahertz. When you match these two frequencies, okay, the input tuning circuit frequency it is a 98.3 megahertz, and the tuning circuit resonant frequency is the omega naught. When these two are matched, okay, these two are matched, so we get maximum current. So maximum current means now we listen the radio Mirchi, suppose in 98.3 megahertz, we clear radio Mirchi signal, catch that signal. Okay, and we that's a no noise, very low noise here, almost zero noise. Okay, and before and after that 98.3 megahertz, so there is some noise. Suppose this diagram now. Suppose diagrams look like this. Suppose that is the 98.3 megahertz, and here we get a maximum current. Okay, so maximum current. Okay, and suppose here 98.9 here, and here 98.9, the current value, okay, maximum current. Okay, now here will certainly drop. So there is a drop, and these drop introduce a noise. Okay, and you get some noise here, and suppose here also the 97.8. Okay, that's a megahertz. Okay, megahertz. Suppose a 98.97 point here. You also get listen the radio Mirchi or any radio channel, but there is also noise because the low noise here, the very very low noise at these omega naught frequency when they are in match, they are in resonant. Okay, and before omega naught and after omega naught we listen that radio signal, but there is some noise, and here is noise is very low noise and clear sound we can hear. Okay, okay, that is circuit is called tuning circuit, and it is a either TV receiver uses and radio. Okay, TV receiver. These are where you use a tuning circuit, very useful here. Okay, and these resonance exhibit only circuit have only L and C component. So here is a very important of the resonance circuit. The circuit is have C and L. These two are the frequency dependent function. Okay, and these C and L always out of phase, always out of phase. That's very important. That's why we use in tuning circuit with the help of L and C circuit, the help of LC devices, okay, passive device, because these two devices C and L always voltage and current are out of phase. Okay, always voltage and current are in out of phase in L and C. Okay, and here is another important part, but these are the excluding our syllabus in 2025 and 26 session. That is the sharpness of resonance. These are the sharpness. Okay, so here we discuss a little bit about the sharpness of resonance. Okay, so the look like the sharpness diagram. Suppose one, and now here we see that here is a IM maximum current. Okay, and this sharp, very sharp. Okay, this here is called omega naught, that's the resonant frequency. And now if I 70% of IM, okay, so IM by root 2 get a IRMS, means 70% of maximum current. Suppose here this line, this line is 70% of maximum current. This line. Okay, here we see that's called omega L, and suppose the low, and this point here is omega high. Okay, and here these two, so these two frequency band, okay, band, these two means omega high minus omega L, and these called a delta omega, and these called bandwidth. Okay, these called bandwidth, means that there is a frequency band, and at that point these two frequency band actually describe, and suppose these are the 98.3 megahertz, and suppose these are called 19 here that's called 99, and if when you tune that circuit in 99.1 and you get zero output here, means a kind, at that point you get only noise, no voice here, okay, in that radio channel. Okay, so and below that suppose the 97, 96, there if you there is a huge noise, means huge noise means there is almost a zero output. Okay, if you listen the radio in very poor quality, the quality is very poor, here quality is very poor, and at that point quality is very high, a good quality, and in between these two you can get also a good quality. Okay, that's why this bandwidth is very important. Bandwidth means that's the gap between two frequencies. Okay, the range of two frequencies is called bandwidth, and it's very important in our home or office. You see that listen that there is a someone say that the broadband, a narrow band. Broadband means the bandwidth is very large. If bandwidth is very large, so maximum number of frequency passes through there. If a bandwidth is very small, there is a very less frequency passing through there. Suppose it look like this. If a broadband, there is a frequency band. Suppose these are the frequency band. It look like this. Okay, and they passes that frequency signals very easily because these are the called a broadband. Now, what is the narrow band? Narrow band means, okay, at that point very less amount of frequency passes through there, and because this is a very small passage, and here the passage is very high, the frequency passage, this frequency passage is very high, and here the frequency passage is very low. So that's why these are called narrow band. That's called a narrow band, and this frequency passes very high. This is called a broadband. Okay, and this broadband frequency is get maximum number of signal are received here. So that's why our download or upload or surfing is very fast. Here is surfing is very slow. Okay, because that the path is very small. Here the path is very high. Okay, that is the concept of bandwidth. Okay, and now, and what is the sharpness here? Now we choose another signal. Suppose here this signal here. Suppose we see that the signal look like this. Okay, suppose these are the another type of signal, and here you see that the maximum current is here. Okay, now you see that the bandwidth, okay, in red color, so we suppose that is IM of red color. Here is the IM by 70% of IM here, so we get that point here. Okay, and that point here, this red color, and see the red color bandwidth is very large, and the red color bandwidth is very large. So in red color, red bandwidth is very large. Bandwidth is very large. Okay, if bandwidth is very large, so maximum current is dropped. So IM is dropped. So IM is dropped. Okay, so IM is dropped means there is a noise here. Okay, there is a not clear cut or quality sound here. You see this radio signal is not a perfectly good quality sound. There is some noise in that signal. Okay, so there is a bandwidth is very large. So delta omega is large than previous. If delta omega is large, the sharpness is fall, and see that there is a sharpness. These are the sharpness is fall. You see that these are the sharpness is very fall, and if you see the previous, the sharpness is very high. You see that this sharpness is very high. Okay, here in the tuning circuit, more sharp means the very important. The more sharp means more current. In get a more current, keep in mind there is a more current means good quality sound. So here is the quality. Suppose the Q quality, that is also equal to omega naught by delta omega. So Q is inversely proportional of delta omega. If delta omega is large, so quality, Q is the quality of circuit is very less. If bandwidth is very large, broadband is quality less, means a less sharp. Okay, there is not a good sharp. Okay, and if you see that is previous diagram here, the bandwidth is very small. If you are very small, a narrow band, and you say the narrow band means quality is very high. If delta omega is very small, this bandwidth is very small, so quality is very high. Quality very high means maximum current is very high. If maximum current is very high means quality of the circuit, a tuning circuit is very high, very good quality tuning circuit. Okay. That's the very important. What is the sharpness of resonance? Is the why sharpness of resonance is very important. Why sharpness of resonance is important? Is important. Clear? So here now we discuss power in AC circuit or power factor. Discuss a power in AC circuit, power in AC circuit and power factor. That's including in our syllabus, and the resonance, sharpness of resonance, that's excluding in our syllabus. Okay, but the discussion is very important. Okay, for a better understanding of what is the resonance or what is the importance of resonance. So here in a power in AC circuit or RLC circuit, actually here it is power in RLC circuit. Here we know that a V, that is Vm sine omega t, and here I current, Im maximum current sine omega t plus phi. There is a phase angle between these two. And now that a maximum current Im, that is equal to Vm by Z, that is the impedance, and the phi we get tan inverse Xc minus XL by R. We get this from previous class. Okay, so what is the power? So power is called average power, that is I times V. So here I equal to Im sine omega t plus phi, and Vm, that is V equal to Vm sine omega t. So Im Vm by 2. Here we get a 2 sine omega t sine omega t plus phi. Okay. Now from class 12 trigonometry, okay, or class 11 trigonometry, I think. Now that's the Im Vm by 2, solving with the help of trigonometry, class 11. Okay, so class 11 trigonometry we solve this, that is the cos function, cos. Okay, so these first, so omega t plus phi minus omega t, okay, minus cos this function omega t plus phi plus omega t. Okay, and now that is equal to Im Vm by 2, cancel these two, cos phi minus cos twice omega t plus phi. Okay, and that's the average power. Okay, so that's why in case of average power, so Im Vm by 2 is very important. Now these are this first function cos phi is a frequency independent function. There's a present here, and that's a frequency dependent function. The full cycle integration of frequency dependent function is 0. We know that. Okay, we're solving 2 or 3 times in previous class, and you see that, and that's why I skip that part. So full cycle integration of frequency dependent function is a 0. So this term is a 0 here. So you get power equal to this Im Vm by 2 and cos phi. Okay, and now just little bit more about Im by root 2 and Vm by root 2 times cos phi, and this Im by root 2, that is RMS, that's also a VRMS. So put that is equal to I capital, say that is V, and here is the cos phi, that's the power, and that is equal to V, suppose I, and V equal to IR, and here the R is now in LCR circuit, there is a Z impedance, so that's why R is replaced by Z cos phi, and final expression we get I square Z cos phi. And you see that very carefully, the power equal to I square Z and another factor here, that is the cos phi factor. So mainly the average power here dissipate not only that a voltage on current. Okay, this average power not only depend on voltage and current. Okay, you see that very carefully, that average power is not only depend on current and voltage, also depend a cos phi factor. Okay, given a cos phi factor. Okay, the phase angle between them. Okay, so this power not only depend on voltage and current, also depends on phase angle. So here this cos phi is called power factor. Power factor. Cos phi is called here is a power factor. So here we change the phi and we get a various type of conclusion here. Suppose we apply some condition here. Suppose the case number 1, suppose say that is cos phi, okay, value when that is phi equal to suppose 0. So phi equal to 0, so cos phi with the 1. So cos phi with the 1 means no phase difference. No phase difference. So no phase difference means the circuit is purely resistive circuit. No, because in AC voltage applied on resistor, so there is a no phase difference at that time. So that's why the circuit is purely resistive. Okay. Now case 2, and if you have phi equal to pi by 2, here phi equal to pi by 2, okay, that means, okay, so inductive or capacitive circuit. The circuit is a purely inductive or capacitive because there is a phase difference between voltage and current is pi by 2 lead or pi by 2 lag. Okay, voltage either lead or lag. Voltage either lead or lag respect to current. No, sorry, either pure inductive circuit or pure capacitive circuit. The circuit is inductive or capacitive, actually depending on that the phi is lead or lag. Okay, voltage is leading or lagging, that's depending on what type of circuit, inductive circuit or capacitive circuit. Okay, inductive circuit or a capacitive circuit. Now at that point when cos phi with a pi by 2, here the cos phi, now so phi we have pi by 2, so cos pi by 2 means cos 90 with a 0. If cos 90 with a 0, we see that is average power with a 0 watt. So power with a here 0. Okay, but the current flowing to the circuit, basically there is a current, but power with a 0, so that power is called wattless power. Wattless power. These are called wattless power. Okay, current obviously there, but the power is 0, that power is wattless power. Okay, now case number 3 here. Suppose in series LCR circuit, in series LCR circuit, the phi that is equal to tan inverse, we know that xc minus xl by r. Okay, the phi may be the non-zero term. Okay, the phi is a non-zero term. So non-zero term means RL, RC or RLC circuit. Such power, okay, such power dissipated only resistor at that point. Okay, here the power, so circuit is look like a RL, RC or RLC circuit. Okay, the power dissipated only in resistor. Resistor. And last, number 4. Here the number 4, series LCR circuit at resonance. Series LCR at resonance. At resonance means, so XC minus XL equal to 0. So that times pi equal to 0. So here cos phi equal to 1. So power, that is also I square Z here. So maximum power, that's the maximum power. Keep in mind, that's the max power. Okay, max power dissipated through circuit. Dissipated through circuit. Max power dissipated through circuit via resistor or via R. When at resonance. At resonance. Okay, that's our syllabus. Okay, so if you have any doubt, please ask in comment section. I will try to give the answer. Okay, so we take too much time, so today end the class here. Thank you.